It's just we don't notice, because it's so small, we don't really notice it in the macroscopic, the large world, but we certainly do on the microscopic world. And the formula that chemists use, known as a Schrodinger equation, a Austrian by the name of Schrodinger, the rather interesting life, kind of came up with it. And I'm just going to go ahead and give you kind of the reduced version of it. Okay, so H hat psi equals E psi. Basically what this is this is a way of treating the electron like treating the wave-like characteristics of the electron. This right here is just known as a Hamiltonian operator. And I put information about the kinetic energy and the potential energy into that operator. And that operator then operates on this little thing called psi here. It looks like a pitchfork. Now, this is not multiplication. It's not multiplication. It's actually operating on it, which is it can do very complicated mathematical things to this little thing called psi here. It's not multiplication, it's actually operation, which is a bit more complicated. Now this thing here, this thing psi, the Greek alphabet, is also called a wave function. A wave function. And the wave function is a incredibly complicated mathematical concept that treats the wave-like characteristics of an electron, but it also takes into consideration the particle-like when we talk about mass, and you can even look look up something called the Broglie Wavelength, where Broglie actually developed this whole concept of a particle, something with mass, having a wavelength associated with it. But basically what the wave function is some sort of physical representation of the electron. So when we have this energy, this kinetic and potential energy, and that kinetic and potential energy acts upon the wave function, what we get out of the formula are these two things here. We get this E, which is a constant, and it's a type of energy called binding energy. And that is the energy that binds the electron to the nucleus. We take a real simple model. We know that the electron is negative, the nucleus is positive, and there's some sort of binding going on. And that energy, depending on which period I'm in, is going to change. And obviously how many electrons are floating around, buzzing around. And then we also solve for the wave function. And this tells us really interesting information about the electron. And what it tells us is, for our intents and purposes, it gives us something called an orbital. Something called an orbital. Okay? Alright, I'm going to go ahead and erase this now. Alright, so there are 4 numbers called quantum numbers that kind of fall out of that whole equation there. There is number N, L, M sub L, and then M sub S. Now, these 3 numbers come directly from that equation, and this one was actually tacked on a little later on. Now, the N number right here is the principal quantum number, the primary quantum number. And wouldn't you know that the N number tells us what shell our electrons are in. If N equals 1, we're in period 1 on the periodic table of elements. Pretty cool, if you ask me. Pretty cool that this periodic table was developed by a Russian scientist, Mendeleev, I believe, well before we figured any of this out. And he just arranged atoms by their mass number, and lo and behold, we have correlation now. So N equals 2 is the second shell, 3, third shell, 4, fourth shell, and so on and so forth. Okay, that's cool. So that's our shell. But there's a little more to it now. And what we have is this L number, very important for our cases. And this explains something called an orbital. An orbital. The M sub L, the magnetic number, basically represents how the orbital is oriented, the orientation of the orbital. So some orbitals may be oriented like this, like this, like this. Just depends on whatever that number is. and this is something called spin, and perhaps I'll talk about it a little later on. But as you can see, there's more depth. Not only do I have a shell, but inside of that shell I have these things called orbitals, and in the next video I'll talk a little bit about orbitals. They're not exactly what you think. They're not orbiting, not an electron orbiting, they're an orbital, and they're actually statistical in nature, and these are going to play a big role